Today we're going to look at finding the electric field of any one-dimensional charge distribution. We'll do it using Sympy to do all the mathematics, and then we'll use numerical packages in Python like NumPy and SciPy to actually evaluate integrals that you can't do by hand. Let's cue the intro and let's get started on the video.
Music's coming back. Did you miss me? We electric like a field. You can call me Big E. We're leaving Griffiths in the dust now with my PC. Gauss's law? Ha! That's so pre-21st century. Sure, it makes you feel like a G when your problem's easy. Life ain't a sphere though, bro. Come and see. For example, consider this here spring in 3D. Gather round and relax, listen to Mr. P.
So like in the previous video I made on E&M, I'll be using the Plotly library today. We're going to be making 3D plots of electric fields, and they're going to be interactive so that we can actually zoom in and zoom out and go around. It's really difficult to make a good vector field plot, and I find that this is the best library for that. Other than that, of course, we got NumPy, SciPy, and Sympy. So a little bit of math before we start. You've probably learned in any E&M course that you've taken that the electric field is given by 1 over 4 pi epsilon naught. This is just a scaling factor. 1 over, so this is like r minus r prime over r minus r prime cubed. That's like the 1 over r squared law. I like writing it in this form because r is where you are. R prime is the location of the charge, times dq. So dq is the amount of charge at r prime. And you integrate over all of r prime and you integrate over all of q, and you get a sort of sense of the total charge, and that gives you the electric field, right? And so the challenge here, of course, is finding out what is dq. As you sort of, scroll through r prime and you go to all the different locations of r prime, and you'll see what I mean by that in a minute. What is the location of dq at that position? Now, there are multiple sort of things that you can have here. You can have one-dimensional charge distributions like a wire. You can have 2D surfaces of charge. You can also have 3D volumes of charge. And so we'll focus on one dimension today. Eventually, I'll make some videos on 2 and 3 dimensions. But in one dimension, dq is equal to lambda. Lambda is a function of r prime. Lambda is the density of charge. So you give me an r prime, there's a wire, and r prime will point all along the wire. You give me r prime and I'll tell you what lambda is there. And most of the time lambda is constant along, any sort of thing here. So that might just be lambda, no function of r prime, times dr prime. This is like the length, infinitesimal length of the wire. And this is really not good to deal with in math. So instead you use dr prime dt. You parameterize this curve in space through t, and then you take dr prime dt, and then you can integrate over this, not so difficult. In 2 dimensions, there's a sort of a similar analog. You have a 2-dimensional charge density now, infinitesimal area element. The infinitesimal area element is given like this. So now r prime, which points to a location of a surface, is parameterized using 2 things. 2 dimensions, 2 things you need to parameterize the surface, u and v. In 3 dimensions, your infinitesimal charge is given by this volume charge density times your infinitesimal volume, which can be dx, dy, dz, or it can be r squared dr, sine theta, d theta, d phi, like pole or spherical coordinates, and there's also cylindrical coordinates, and there's many sort of coordinates in 3 dimensions. Now the challenge is solving for dq, so we'll focus on this today. We'll go through 2 examples. What we're going to do is we're going to do it entirely using a computer. We'll use Sympy to come up with the integral, and then we'll use numerical techniques to evaluate the integral. Then we'll use plotting to make a nice plot of the field. Now, numerically, and I talk about this every video, making the problem dimensionless, because it's really annoying to deal with dimensions on a computer. And you'll note that if the electric field is given by something that looks like this, this means that the following quantity, where I have an r squared and a q here, is dimensionless, and I have a little subscript d on everything. All the variables with the subscript d are dimensionless. That means they have no units. They're like numbers, right? And so that would be a dimensionless position, which I talk about in my videos as just being like, how many R's is something. So if RD, if the magnitude of this is 4, it says that there are 4 R's, for example. That's the characteristic length of the problem. And Q, the characteristic charge, is related to the charge density, right? You'd have to specify this in some way as well, but the easiest one to understand is the characteristic length R. And so if the magnitude of RD is 3, that just says it's 3 R's big. So in the problems I'll look at today, I'm going to omit the subscript D. It obviously gets a little bit messy. And all quantities are going to be assumed to be dimensionless. That means we can set R equals Q equals 1 in all problems without loss of generality. I encourage you to think carefully about what that means here. It means we can deal only with dimensionless things, and that tells us everything we need to know about the geometry of the problem. And the magnitude of the electric field is just scaled by adjusting R and Q here after the fact. So our first example is going to be a spring of charge, and I'll plot this later. It's got a ring radius R equals 1, and it's located at the following position. So it's cos 4t, sine 4t, and t. If t were equal to 0 here, that would just be a circle that goes around a few times, right? Cosine, that's a parameterization of a circle, but it also increases with z, meaning that it twirls upward. For 0 is less than t is less than 2 pi, with total charge q equals 1, and charge evenly spread across. So it's a spring of charge, it's one-dimensional, and it's got a constant charge density. Plot the electric field and charge. Okay, so the step 1 is finding dq. That's always the first step in these problems. That's the most difficult one, since it's not really done using a computer. You sort of have to think about it. So since we're in one dimension, I already told you that dq is equal to lambda of r prime, dr prime dt, dt. And see how, this is what I mean by r prime being parameterized. I give one sort of variable here, t, and I can plug in any value of t, and it will point to all the different locations on the spring of charge here. So you give me t, I'll give you a location on that spring. Lambda is constant. Lambda does not depend where you are on the spring. It's constant the whole time. So I can remove this dependence on r prime. Dr prime dt, you just take the derivative of that. That's pretty easy. Using the fact that the total charge is 1, so q equals 1, integral of dq, that's the integral of this, and I pull lambda outside because it's constant. I can find that lambda is equal to this inverse just by dividing by this integral. That tells me what lambda is here. So let me import all the packages today. So I define my variables, t, because I'm going to need that to parameterize the charge, and x, y, and z are going to be our field point, right? There'll be different field points for the charge. So that's the test point r, x, y, z. The location of the charge r prime depends on t. So r is equal to x, y, z. That's our test point where we're testing what the electric field is. And r prime is the location of the spring of charge given by the same formula up here. The separation vector, which I call sep, is r minus r prime. That's typically handy to define. The test point minus where you are on the charge, and there's a vector that sort of points between those 2 points. Separation vector. So I can define these quantities, and I look at r, it's just x, y, z. R prime is the, my god, I can't type today. R prime is the location of the spring, and then separation will be the difference between these two. So I have everything just slowly building up with Sympy functionality here. Of course, I use the simp.matrix to define vectors. Very helpful. Now we need to solve for lambda, which is the inverse of this integral. So to do that, we need to, of course, get the component dr prime dt. And I want to do this all in Sympy. Obviously, this isn't very difficult to get the derivative of, but doing it in Sympy is proper. So you'll note what I do is I need the absolute value of this, which, of course, is the norm of the vector. So if I can differentiate this with respect to t like this, I use the simp.diff method. It'll take the derivative of this. Again, not super difficult to do by hand. Then I can get the norm by calling dot norm. This will take the length of this vector, which is what we need. And then I can simplify it as well. And it'll, of course, note that sine squared plus cos squared is equal to 1. And so it will do all this simplification. It's actually a very nice simplification here. And I need to integrate this from 0 to 2 pi. Of course, that's, again, trivial to do. You're integrating a constant. You just get a number itself. So I define this quantity, and I integrate this quantity, t, from 0 to 2 pi. Note the notation here for simp.integrate. And I print lambda, of course, here, and it's 2 root 17 pi. So that's what my charge density lambda is. If q is equal to 1, then lambda, even though it's constant, is equal to 2 root 17 pi. some complicated sort of irrational number here. And that's sort of worth noting is that, although your characteristic length and charges are pretty simple, it has ramifications for things like the charge density. And now we define the integrand given like this, and you think, where does this come from, this integrand? Well, note the form r minus r prime over r minus r cubed, lambda dr prime dt. That's essentially this integrand here if I plug in dq is equal to this. So if I plug in dq is equal to this and put this up here, then that's exactly the integrand that I talk about down here. So we need to define this integrand, and we're going to integrate over all of t. So the integrand is equal to lambda times separation vector. Remember, separation is r minus r prime divided by sep.norm cubed. So this takes the norm of this separation vector and it cubes it, and I times dr prime dt, which of course this is the norm, right? Dr prime dt, I already called norm.simplify. So this is the absolute value here. And then I can look at my integrand, and it's sort of a complicated expression. And of course, to find the electric field, I need to do like 3 separate integrals to get Ex. This is the Dex, right? Dey, the differential of Ey, and Dez. These are the 3 things I need to integrate. You'll note that it's a function of t. I plug in a value of x, y, z. It integrates over all t, and then I get a value for my electric field. So I need to do this with this integrand. Now, this is where I stop using Sympy, and we have to use a numerical library of Python to do this, right? And so what I do is I have this symbolic expression in Sympy that I convert to a numerical function in Python. So I have dex dt, right? This first component, and there'll be like a dt, of course, at the end here as well. So dex dt is simp.lambdify. You'll note that it's a function of t, x, y, and z. I choose a value of x, y, z, where I want to test my charge, and I integrate over all t. If I want to make a plot of the electric field everywhere, I'll need to do one integral for one xyz, another integral for another xyz, and go like that. But for now, I'm saying I'm creating the simp.lambdify function, txyz, and I say, okay, I want the first component of my integrand. So integrand is 0, for example. That just returns dex dt. And so what this does is it creates a function, and it's just the same thing for y and z. So I give a dex dt, and suppose I'm at 1, 1, or x equals 1, y equals 2, or it starts with t actually. So t is equal to np.pi. Remember, t goes from 0 to 2 pi. And I'll say I'm at x equals 1, y equals 2, and z equals 3. And it will return this value. Now, this might have to do with some symmetries here. In fact, there might be nothing, so I can plug in this value here. Remember, sometimes there's no contribution, but here at t is equal to np.pi, and these values of x, y, z, I get a specific value for dex dt, and that's my function that I need to integrate over from t from 0 to 2 pi for many different values of x, y, z. One x, y, z will give me one electric field. So dex dt, dey dt, dz dt, I need to integrate these numerically. I just create a function that returns the electric field, E of x, y, z, right? So that it will integrate dex dt, integrate dey dt, and integrate dez dt using SciPy's quad function. So what quad does, and I'll show this sort of separately. So I say I want to take my function dex dt. I'm going to integrate from t from 0 to 2 pi. That's exactly what I said. It goes from 0 to 2 pi here. The args are x, y, z because I need to specify x, y, z separately. Remember, I specify one point, I integrate over, and I get the electric field at one point. That's why my E here is a function of only x, y, z. And I can do this, for example, and I need to actually give 3 arguments. So I'll go like 1, 2, 3, for example. And it will integrate dex dz at the location x1, y2, z3. And of course, typically when you call quad, it gives the integral and then also the error on the integral. So I just take the first component and I get my integral of dex dt. So now I know what ex is at this location. And I do this for ex, ey, ez, and I store them in this numpy array. So this function e of x, y, z is really nice because I can give it any point that I want, and it will return me the components of my electric field. So no matter where I am, I can find the electric field. But what we want to do is we want to create a 3D plot of the electric field everywhere. So I need to loop through a bunch of x, y, z values and find the electric field at all those different locations and then make a plot. So in order to do this, we need to create a mesh grid of X, Y, Z points to solve for this. If you're unsure of what's going on here, I'd recommend you check out my NumPy tutorial video. I talk about what mesh grids are and how they can be used to find 3D sort of functions and why it's important, especially when plotting 2D heat maps, for example. But anyways, I use the mesh grid here. And using the mesh grid, I can compute the electric field at all points. And to do that, I use numpy.vectorize, and now that will automatically create a loop. But it takes in this function e, right? And you'll note that there are 3 arguments to e, x, y, z. So it will pass x, y, and z, and it returns e field, one particular thing. So you need to specify this signature thing because it's taking in 3 arguments. It takes in xv, yv, and zv, and it will loop through that mesh grid and find the electric field everywhere. So if I just run this cell before I actually get into E, X, E, Y, E, Z, remember it's solving for the electric field everywhere, so it takes a little while. I can look at E field, and this will return my X component of my electric field everywhere, Y component, and Z component of the electric field everywhere. And to get the X components only, the X is at the last axis, the 0th element. So there are 4 axes here, and I take the last element here, and that gives me EX. And if I take this, you'll note that these arrays are 3D because it's a 3D array where, you know, you have a point and it tells you what's the EY field. So the first one is you have a point, it tells you what the EX field is. Same thing for EZ. That's how I extract my components here. Again, I recommend if you're unsure of this, look at my NumPy tutorial video and make sure you understand how array indexing works. This is important for dealing with these sorts of problems. And then I can, you know, look at the electric field at all locations because now I have EX everywhere, EY everywhere, and EZ everywhere. But I want to look at how the electric field varies over this mesh grid. And you'll note that there's some variation here, right? I mean, sometimes, or like, you know, EX, for example, it's sort of, they're all centered around 0. So sometimes the electric field is pointing in the right X direction, positive X direction, sometimes to the left X direction. Same thing with Y and Z. So this is like a histogram of the electric field, X component, Y component, and Z component here. And the reason why I'm looking at this is because every now and then you'll get a test point that's really close to the source of charge, and you have like a really big electric field. For example, here, like you have one point that's really large. That just so happens that you have a test point that's close to, in this mesh grid here, of X, Y, and Z's, all the points you're testing. It's really close to the charge distribution, and so you get it kind of blowing up. And so when you're making a plot, you don't want really large arrows. So what we do is we make a cutoff. We say, I don't want really large field values, so I'm going to make a cutoff at 150. And everything that's larger than 150 is going to be set equal to 150 so that we don't get these really large arrows on the plot that kind of make it look unaesthetic. And that way, you know, we still get a sense of the geometry of the electric field, but we don't have any, like, you know, gross looking things on the plot. So here I set Emax is equal to 150. I don't want anything really bigger than that. Remember, it's all dimensionless. And anything that's bigger than 150, I set equal to 150. Anything that's less than negative 150, I set equal to negative 150. Now I compute the line, right? Remember, we have that spring of charge. So my t's, of course, go from 0 to 2 pi, and x, y, and z locations of the spring of charge is cos 4t, sine 4t, and t itself. That's my x, y, and z. And now I can make this 3D plot using the Plotly library. So for my electric field, I use a cone plot. I have to give my mesh grids, and I unravel them using the ravel method. Same thing with EX, EY, and EZ. Everything has to be given in a 1D array. And there are arguments here that I recommend you look at. This is sort of how to deal with this. I also specify the layout of the plot here. And then I create a figure. And on the figure, I also add the actual charge spring itself, like this. And I add it in green so you can see it. So everything I'm talking about now, you'll see, again, study this code. It's important. And now you see that my spring of charge here, like I was talking about, and the electric field. And it's interactive, right? If I just showed a picture like this, it would be very difficult to see what's happening. But because it's interactive, it's really nice. I can zoom in, I can look around, right? And you'll see that, you know, it's sort of what you expect of the electric field or a charge, right? wherever there's a charge, the electric field is pointing outwards from it because everything is positively charged. So no matter where you go on this plot here, the arrows will be pointing away from the green. That's sort of the divergence of the electric field. It diverges away from charge. And you can see it here too, all the cones sort of pointing outwards. Sometimes it's a little confusing what they do, like right in the center, for example. It's pretty small electric field in the center. And furthermore, if you zoom out on the outside, you get this sense that it's all sort of pointing away from the spring. And if you're really far away from the spring, of course, it's just a monopole. And it looks like a point of charge. If you're really, really far away from the spring, it looks really, really small. It's like having a point charge. But of course, the thing that's nice about this too is you can get right up into the spring and see what's going on. I have one more example today, and I'll go a little bit quicker through it, but it's also a useful one. It's a dipole charge. So there's a charge density located like this, t squared 0. If you're curious what that is, that's a parabola. So it's a line of charge that's in a parabola from -1 to 1. And it's got a linear charge density, a times t cubed. So when t is negative, right, on the left side of the parabola, you have negative charge there. And on the right side, you have positive charge. And it overall creates a dipole charge. It's just a weird looking dipole charge. And there's a proportionality constant a here. And it's a dipole, of course, so the net charge q net is equal to 0. But it's such that the charge on each side of the dipole is q equals 1. So this is the reference charge here. Remember, there's the reference length r. So reference length r might be the arc length of the parabola, for example. But here the reference charge is q equals 1, such that q equals 1 exists on each side of the dipole. So again, it's a very similar procedure. I define t, x, y, z like I did before. Define the test point, the separation vector. What we need to do now is we need to find this symbol capital A here, right? And so what I can do is, using the fact that capital Q equals 1 on each side of the dipole, I have 1 over A is equal to this. So ignoring the A, suppose I multiply both sides of this equation by A, I have 1 equals lambda of t dr prime dt dt. That's just saying that capital Q is equal to 1. Then I divide both sides of the equation by A to get this expression here. And I can actually solve for lambda of t divided by A. That's just t cubed. So I have t cubed. I can solve for this dt. So I can solve for everything on the right-hand side. Even though I don't know A, the divide by A gets rid of the A. So I solve this on the right-hand side here. And then I can rearrange it to get A from the left-hand side. So I get lambda over A is equal to t cubed. That's what I have up here. I need to solve for this dr prime dt. I have A is equal to this integral to, inverse to the power of -1, right? Because I multiply by A and then I divide by this on the other hand side. That's solving for A. And I get lambda is equal to A times t cubed. And doing this, my value of lambda, so A is equal to 1 divided by 1 over 120 plus 5 root 5 over 24. Something that probably would be kind of annoying to integrate to get in person. Then it's the exact same procedure as before. It doesn't matter that the charge distribution is different. We have lambda dr prime dt and everything else. And I can run through all the code, same procedure like I did before. So like before, I can look at the histogram of the charge, and I see that, 2 is basically the maximum here. And I actually choose 2, which is like a little larger than most of the charge, because I think it looks a little bit nicer on the plot below to see what's happening. But I don't want anything too big, or it's just going to look a little messy on the plot. So my maximum electric field magnitude, I'm going to cut off at 2, so I don't get any big cones. I do that through here. And making the plot like I did before, I get the following plot here of the dipole, and you can see my parabola in the plane, the xy plane. And you say, okay, well, how does it look exactly like a dipole? Well, here's the positive charge n, and you can see that the electric field is sort of diverging out here of the charge, whereas the negative end, everything is sort of diverging in because it's negatively charged. And if I sort of pull back here and look at the right angle, you can see that it's exactly the electric field of a dipole that you expect. It sort of diverges. If you have a positive and negative charge, it's diverging out. The electric field sort of goes from here to here in the center, and you get this dipole field on the outside. And again, if you're really far away from this, sort of out here, it looks just like by the way, a lot farther away than this. But if you get really far away from this dipole, it just looks like a true dipole, right? When you're infinitely far, you have a true dipole field. And so this electric field on the outside becomes that of a true dipole field when you're far away. But again, this plot allows you to sort of get in and see these weird distributions sort of up close, and you can look exactly at the arrows and get a pretty good geometrical idea of what's going on here. So I hope you enjoyed this video. We'll be looking at 2D and 3D in the future for electric fields. Again, we'll be dealing with these sort of plots as well because they're very useful to sort of qualitatively look at electric fields. If you liked the video, please be sure to like and subscribe, and I'll see you next time.